High frequency line trap. Line trap is a solenoid which inductance is used to filter high frequency signals. Line trap is connected in series with a transmission line. In a line trap, conductor is made of aluminum and fixed in the fiberglass case. Line trap should withstand electrodynamic forces that could appear during transmission line short circuit. Our task here is to calculate forces and mechanical stresses in the fiberglass case. Stranded aluminum cable cross-section is 20 mm squared. Peak current value is 20 kA. AC frequency is 50 Hz. Fiberglass case diameter is 700 mm. The height is 468 mm. Aluminum Young's modulus is 70 gigapascals. Aluminum Young's modulus is 70 gigapascals and fiberglass Young modulus is 20 gigapascals. The geometry model features rotational symmetry and we will simulate it in two-dimensional axisymmetric setup. Okay, let's start QuickField now. In QuickField I create new problem. Problem name is trap. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem pane and on the right you can see the geometry model editor window. You can draw the geometry model here or you can import the geometry model from the AutoCAD DXF file. Here I have the file open and the geometry was imported. You can see the cross-section of the trap solenoid. In the axisymmetric problems, the axis of the rotational is a horizontal one, and we should draw only the upper half of the cross-section. So switch to select objects, select everything located below the axis, edit, delete selection. Yes. Now here you can recognize fiberglass case and aluminum cable. Let's assign labels. The labels will specify material properties. Switch to select objects mode, select with the rubber band and assign a label to these blocks. This is the fiberglass. Inside the fiberglass we have the aluminum conductor. Again select with the rubber band and these are aluminum. Inside the solenoid is the air. Now we can click the labels and find out which objects correspond to the specific label and assign physical properties. Double click the label name in the tree and for the air I specify a relative magnetic permeability which is 1. Okay. For the fiberglass again relative magnetic permeability is 1 and 0 electrical conductivity. Okay, for the aluminum I specify permeability, electrical conductivity which is 37 megasiemens per meter and the total current which is, and I should specify that conductors are connected in series. Okay. In fact, the magnetic field is distributed not only inside the solenoid but also in the air outside. QuickField cannot simulate infinitely large space, so we need to restrict the simulation domain. Zoom out, switch to insert mode, the line type is the straight line, and draw the horizontal line along the rotational axis. Now change the line type to be the half arc and draw the half circle. Switch to Select Objects mode, click here to select the air outside and assign the label air. That's all for blocks. Next we should assign labels for boundaries. QuickField automatically assigns proper boundary condition on the axis of the rotation. And I believe that far from the solenoid magnetic field fades to 0, so I assign label 0 field to this boundary, and for this label I specify 0 magnetic potential. Okay, model and data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and run the analysis. The problem has been solved and we can take a look at the results. Here you can see the magnetic field lines and the column map of the electric current density. You can adjust the field picture and switch on the color map of the magnetic flux density. The correspondence between colors and numbers are shown in the legend, and you can get exact values using the local values tool. Just click any point and you can get the flux density, the magnetic field strength, the current density, if any, and other parameters. You can edit the coordinates here. You can also use the contour tool to construct XY plot. For example, here I click the axis and get the flux density distribution along the solenoid axis. The numbers you can see in the table: coordinates, flux density, and other parameters. You can also draw any arbitrary contour, the same way you draw lines in the geometry model editor. And you can use contours to calculate integrals. Contour clear, zoom in, and click inside conductor. Follow to the integrals, total current, which is 12 kiloamperes, joule heat, magnetic force. So we come to the next task: calculation of the mechanical stresses in the solenoid case caused by the magnetic forces. QuickField allows to simulate multi-physics problems, and I would like to pass magnetic force distribution from AC magnetics problem to stress analysis problem. That is done through the problem linking, but first I should create the stress analysis problem. Create new problem. Problem name is trap stress. Next, problem type is stress analysis. Model class is axisymmetric. Length units are millimeters. To be able to pass data from one problem to another, both problems should be based on the same geometry model file. So click Browse button here and locate the geometry model file that I used in AC magnetic analysis. The geometry model file name is trap.mod. Here it is. Open. Finish. So the geometry model is the same and we have already assigned the labels. Now we should provide mechanical properties to these labels. we do not calculate mechanical stress in the air, so for the air I do not specify any values, just open the dialog and click OK. Now instead of the question mark we can see an exclamation mark. This mark indicates that this label is not an unknown label. It is a label with empty dataset, and this label is excluded from the simulation analysis intentionally. Okay, for the aluminum, the Young modulus is 70 gigapascals, and the Poisson's ratio is 0.34. Okay, for the fiberglass, the Young modulus is 20 gigapascals, and the Poisson ratio is 0.11. Okay. The external boundary with zero field has no physical meaning in stress analysis problem. Again, I open label properties dialog and do not specify any values here. Just click OK. Now you see the label has the 0 mark. We have finished with the material properties. Now let's set up the link. Open the problem properties and follow to the links tab. Here choose the imported data type, magnetic forces. Browse for the magnetic problem file, which is chap.pbm. Here it is. Open and add the link. OK. Now the link has appeared in the tree and we can start the multiphysics analysis. Click Solve. Yes, save all simulation files. And we've got an error message, not enough boundary conditions. What does this mean? There is magnetic force acting on the winding, but there is no restrictions to the winding displacement. The construction looks symmetrical, so let's assign label to this point in the middle, and for this point I will specify 0 horizontal displacement. Okay, now we can solve the problem, and we get another error message. The linked problem results are out of date. Indeed, we have modified the geometry model. We have assigned new label to this vertex, and we have specified physical properties in stress analysis problem for this vertex. But no properties are assigned in the magnetic problem. Okay, this label has no physical meaning in magnetic problem. I do not assign any data here. Just click OK. And we should run the simulation process again. The magnetic problem is simulated. We can proceed with the stress analysis. Yes. No more error message this time, and we can take a look at the results. Here you can see the deformed shape of the solenoid trap. In fact, this shape is scaled many times, and you can switch on the color map of displacement, and you will see that the maximum displacement value is within few micrometers. Now let's check the mechanical stress distribution. Switch on the color map of the stress, principal stress. Okay. You can zoom in, and you can use the local value speaker to get the exact value in any point. Or you can use contours to select the edges and see the stress distribution on the XY plot. If you search for the line trap on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.